In this video, we're going to start looking at some of the concepts that you need in order to understand and explain periodicity. And when I say periodicity, that means explaining the different trends that you're going to start to find on the periodic table, like atomic radius, ionization energy, electronegativity, yada yada. All of this is really going to tie back to the Coulombic force of attraction between electrons and protons in your atoms. So we're going to look at what's called Coulomb's law, and that's when I say Coulombic force of attraction, that's who I'm referring to, Coulomb. Okay, so Coulomb, he looked at how the two charged objects interact with each other and the force of attraction, or the electrical force of attraction between them. So, and if you remember, we did a little demo with this with playing with magnets, and we started to talk about what are the different factors that are going to influence the force of attraction. So the two things that we came up with is two things: charge. Okay, so we said that if you remember our magnets, when we held them together, we tried +1 -1, when we tried +3 -3, we felt a much bigger attraction between the +3 and the -3. So he and Coulomb found the same thing. He saw that the force of attraction is directly related to the charge on the objects, and we're going to give charge the symbol Q for now. And he also discovered that it's going to be inversely proportional to distance. So if you remember, when you're holding up magnets, you feel this force of attraction between the two magnets a lot more when you hold them closely, and you barely feel it when you hold them very far apart. So he found that the force of attraction between two charged objects is inversely proportional actually to the square of the distance. So the distance has a really big impact here. He put this together in what's called Coulomb's law. And this is not on your it's not on your formula sheet. It's not even an equation you're ever going to have to plug into. You just literally need to know the implications of it. You need to know that the force of attraction between two objects is going to be directly proportional to the charge, and it's going to be inversely proportional to the distance, or the square of the distance to be exact. And this is something you probably will use a lot in physics and plug into and actually get actual values, but we're really just going to deal with it conceptually in chemistry. And I just want to show you K, this proportionality constant. Look at what a huge number this is. All I want to show you is that this magnitude of K means that these forces of attraction are going to be really, really strong, and they're really going to dictate what's happening with these periodic trends here. Okay, so this is the summary of what you actually need to know. If you want to memorize that equation, feel free, but you don't have to. You need to know that the Coulombic force of attraction, and that's why I just put an FC to abbreviate for the Coulombic force of attraction. Or you can just say force of attraction, but since Coulomb was the one who came up with it, I'm calling it Coulombic force of attraction. And if you're on the AP exam and you write Coulombic force of attraction, they're like, ooh, that looks good. So the Coulombic force of attraction between the valence electrons and nucleus, or any electrons really in the nucleus, is going to increase as the charge of the nucleus increases. So that's a big selling point here. The more protons that you have in your nucleus, the more they're going to attract the different electrons. The first energy level might get pulled in more than the first energy level in something that has less protons. Okay, so charge is going to be a big factor here. Another big factor is distance. Okay, the Coulombic force of attraction between the electron and the nucleus is going to go down as the distance between them increases. And this is going to be another huge factor here. So if you remember, electrons are spaced into energy levels. So the further and further these electrons are from the nucleus, the less they're going to be attracted to them. So it's going to influence things like they're going to be easier to be removed. So it'll be easier to form a positive ion. It's going to be less attracted to the nucleus, so it might be more likely to be reacted if it's a metal that loses electrons. So we're going to really see a lot of these different trends that we're going to observe are going to tie down to two different things: charge and distance, and how they affect the force of attraction between the oppositely charged things in your atom, which are protons and electrons. Okay, so again, that equation's not on your formula sheet, but you do need to know these relationships. Bigger charge, bigger force of attraction. Bigger distance, smaller force of attraction. Okay, remember that like charges repel and opposite charges attract. Okay, so if you're ever trying to figure out or explain a trend on the periodic table, you are coming back to this force of attraction. You're explaining it in terms of Coulombic force of attraction and what's happening in terms of charge and or distance. So let's talk about charge. So a lot of times we're going to be looking at what's called the effective nuclear charge. For shorthand, you can write ZEFF. Some sources even do a Z with a star. If you're writing this on an AP free response, make sure to actually use the whole term effective nuclear charge, and then you can use a symbol once you say that, effective nuclear charge, ZEFF, and then use ZEFF again. But the effective nuclear charge is the net charge experienced by an electron in an atom. So depending where that electron is in your atom, if it's in the first energy level, the second energy level, so on and so forth, it's going to feel a different charge from the nucleus because there's going to be some electrons in the way that we call shielding electrons. So that's why we use this term effective. It's used because of the shielding effect. If you have core electrons, they're going to block the outer valence electrons from feeling that full nuclear charge. So core electrons, remember, are generally closer to the nucleus, and they can help shield valence electrons. So how can you figure out what the effective nuclear charge is? Let's just talk about conceptually. So the term shielding refers to the act of inner electrons blocking outer electrons from feeling the full nuclear charge. Effective nuclear charge is the term that means the charge of the nucleus that the electron actually experiences. So if I'm looking at potassium, and here's the electron configuration out for potassium: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If you have trouble with that, go back to my video about electron configuration. So if we're looking at the inner electrons, okay, these would be the closest to the nucleus, the 1s2, right? The nucleus would be right here, let's say, and the 1s2 electrons would be right next to it. So what about shielding? Would they really experience any shielding? They would have the least shielding. There's no other electrons in front of it that are in the way of the nucleus. So the 1s2 electrons are not being shielded at all. As I get further from the nucleus, when I get into the second energy level, then I would start to have some shielding. Those 1s2 electrons would shield the second energy level from feeling the full nuclear charge. These 1s2 electrons, the electrons in the first energy level, would have the greatest nuclear charge, or greatest effective nuclear charge. They would essentially feel the whole charge of the nucleus. They would feel all 19 protons because they're right up against them. Okay, as you get further from the nucleus, as you go along your electron configuration, 4s1, these electrons in the fourth shell, would be furthest from the nucleus. They would experience the greatest shielding. They would have 2 electrons in the first energy level, 2 plus 6, they'd have 10 electrons in the second energy level. They would have 6 plus 2, they'd have, sorry, not 10. They'd have 8 electrons. 6 plus 2 is 8. 8 electrons in the second energy level, 8 electrons in the third energy level, all of those electrons blocking these fourth energy level, this 1/4 energy level electrons from feeling the full charge. And so this would experience the least effective nuclear charge. So how can you actually calculate effective nuclear charge? All you do is you look up the atomic number, which would be the nuclear charge, because remember that the nucleus holds protons and neutrons, and only protons have a charge. Neutrons have no charge, so whatever number of protons you have, that's the charge of the whole nucleus. And you would subtract out any shielding electrons. Shielding electrons are defined as core electrons, or electrons in inner shells. So any electrons that are in a shell below the one you are looking at. We don't include electrons that are in the same shell or the same energy level, just ones that are below the ones we're looking at. So this is all going to depend on which electrons and which shell we're looking at, and that's why ZEFF will change depending which shell you're looking at. Okay, so let's do an example. Take a moment, try these examples. Which would have a higher effective nuclear charge, Li or Be? And then explain. Why don't you can also try actually calculating it as your explanation. And try the next one as well. Pause the video and then check your work. So Li, if I look up Li, okay, I just wrote the electron configuration so we can look at it. Li has an atomic number of 3, so there's 3 protons. And I want to know about the effective nuclear charge. I'm going to assume on the valence electron. So I really should have specified that in this example. But if I don't specify, we're going to talk about the effective nuclear charge on the valence electrons. So going forward, if I don't specify, we're talking about valence. So my valence electrons are in the second shell. So any shell below them would shield it, and there are 2 electrons in my first shell. So there are 2 shielding electrons, so my effective nuclear charge on that one valence electron would be +1. +1, it would field. Even though the entire nucleus is a +3, the effective nuclear charge, the charge that that valence electron is feeling, is +1. Let's do the same thing for beryllium. Let's talk about what each of those valence electrons would be feeling. So beryllium has 1s2, 2s2 electron configuration. It has 4 protons, so its atomic number is 4, and the nuclear charge, a full nuclear charge, is 4. But there are 2, still also, like the Li, there's 2 shielding electrons because there's 2 electrons in the shell below the second energy level. I'm not going to consider any electrons that are in the second shell because those would be in the same shell as my valence electrons, and they're not going to shield each other. Okay, so only inner electrons. So 4 minus 2 is +2. So beryllium would have a higher effective nuclear charge. And what you'll see is if we go across the periodic table, we're going to start seeing that each of these each time I go across the periodic table for the main group elements, I add 1 to the effective nuclear charge. And you're also going to see that this kind of, hey, as a shortcut, for these main group elements, the effective nuclear charge is really just the number of valence electrons too, but with a positive charge. Plus Li is 1 valence electron plus 1, Be 2 valence electrons plus 2. Yeah, that's kind of a shortcut too. Okay, so let's do the next example, Li or Na. So Li I'm just going to copy from above. It's the same thing, but now I'm looking at Na. Now I'm starting to look at a trend down a group. So as we saw, going across the periodic table, Li to Be, and to the one after it, it's increasing the effective nuclear charge by 1 on those valence electrons. Let's talk about going down a group. So Na, here's the electron configuration. If I look up Na, there's 11 protons, so it has an 11 nuclear charge plus 11 full. And its valence electrons in the third shell. So the first and the second shell are going to shield that 3s1 valence electrons. So there's 2 in the first, there's 8 in the second, so there's a total of 10 shielding electrons. So that's a +1 charge. And as I said, hey, look, it's the number of valence electrons with the positive charge. Okay, cool. What do you notice as you go down a group? The effective nuclear charge is not changing because even though I've essentially added on a whole nother energy level. I have more total protons, but I have more shielding electrons that cancel it out. So this is a really good thing to start seeing. As we talk about shielding and effective nuclear charge, okay, shielding starts to increase down a group. You add an electron shell. Every time you go down the group, you add another shell. So you have more shells and then more shielding, and that's why it didn't really change the effective nuclear charge because even though I've added more protons, I added more shielding electrons as well. So shielding would be an argument down a group. Instead of using shielding, what we can really be talking about is if you're adding an electron shell, you're increasing the distance. And remember that distance is one of those things that affect the Coulombic force of attraction between charged objects. You increase the distance, you decrease the Coulombic force of attraction. So we're going to start seeing that when we're talking about going down a group, we're going to be using a distance or a shell argument. Effective nuclear charge is going to be an argument as we go across a period. You have the same number of core electrons, right? If I kind of go back here, I have the same, as I go across a period, I have the same number of core electrons. I'm just adding valence electrons into the second, more valence electrons into the second shell. So across a period, you have the same number of core electrons, same number of shielding electrons, but you're adding a proton as you go. So the effective nuclear charge is changing and increasing across the period. So whenever we're really comparing things across a period, we're going to be using effective nuclear charge as an argument. When we're comparing things down a group, we're really going to be starting to use a shell argument or a distance argument, or if you even want to talk about it in terms of a shielding argument. Okay, take a moment, try this example, and then check your work. In which atom do the outermost electrons experience the strongest effective nuclear charge? If I notice, these things are all across a period. So I'm going to pick the thing that's at the end of the period. And if I wanted to actually do out work, I can write the electron configuration for all of these things. I can find the number of protons, and I can get the effective nuclear charge, and I'll find that S has a +6 nuclear charge. P is +5, S is +4, or Si is +4, Al is +3. This has the most number of protons for the same number of inner electrons. Okay, in which atom do the outermost electrons experience the greatest shielding? These are all in the same group, but as I go down the group, I have more shielding electrons. If you wanted to, you could write out the electron configuration. You could figure out how many shells each of these things have, and Te has the most shells, so it has the most shielding electrons. Okay. Just as a note, full energy levels, they are, so if you have electrons in the same energy level, like I said before, they are not going to shield each other. So you're only counting inner electrons. Okay, and we are not, if we're talking about like 3s and 3p, 3s we're not going to consider shielding 3p. They are all in the same energy level. They would not shield each other. Okay, let's do another example. Consider a sodium cation, meaning sodium ion with its charge, fluorine anion, fluorine with a negative charge, and a neutral neon atom. Take a moment, write their electron configuration, do it the full long way. Okay, so they would all have 1s2, 2s2, 2p6. Okay, they are all what we call isoelectronic to each other. They have the same electron configuration. So they are isoelectronic. They each have 10 electrons. My question is, would they have the same effective nuclear charge? Take a moment, calculate it for each. Try to calculate it for Na+, F-, and neon. Okay, so for F-, it has 9 protons, and it would have 2 shielding electrons, because only the 1s2, only this first energy level, would shield these outer electrons. We're considering this all as one energy level, 2s2 and 2p6. So it would have a +7 effective nuclear charge. Neon would have 10 protons and also 2 shielding electrons because it has the same electron configuration, so it would be +8. And sodium would have 11 protons, but only 2 shielding electrons, same as the other, so +9. So they don't have the same effective nuclear charge. It makes sense. I have electrons in the same location, but I have a much stronger nucleus. I have more protons in my sodium ion, so it's going to attract those electrons more. And what about its radius? It's going to pull them in even tighter. Okay, so even though each has the same number of shielding electrons, the effective nuclear charge varies because each has a different number of protons. It's protons minus shielding electrons that affect the effective nuclear charge. Which would have the smallest radius? It's really helpful to look at Bohr diagrams sometimes. So even just a visualization of this, you have the same exact electron configuration, 10 total electrons, 2 in the first shell, 8 in the second shell. So you have the same number of shielding electrons, but you've added one more proton in the nucleus going from F- to Ne to Na+. So these outer electrons are going to be more attracted to an 11+ nucleus than they would be to a +10 nucleus than they would be to a +9. So Na+ is going to be the smallest. Its electrons are going to be pulled in the tightest. It's going to experience the greatest Coulombic force of attraction. And F- would experience the least. It would be the biggest of this. And if you go back to that when we observed bright line spectra, and we were talking about how each element has its own unique spacing of energy levels. This is why, even if you have the same number of electrons, if your protons are different, if your nucleus is different, the electrons are going to be attracted differently, and they are going to either be closer or further depending on that attraction. Okay, so this is a really important concept. And we can really use those Bohr diagrams to talk about how these trends change across a period and down a group. So if we go across a period, okay, and like looking at this second row, okay, you've added one more proton to your nucleus, but you have not changed your shielding electrons. So these outer electrons are going to experience a greater effective nuclear charge as you go across a period. You have the same number of core electrons or the same number of shielding electrons, but you keep adding one proton to your nucleus, and that's going to draw my outer electrons in tighter. It's going to affect a lot of different things like radius. It might pull the radius in more. It's going to affect things like ionization energy. It might be harder to lose electrons if those electrons electrons are closer and more attracted to the nucleus. So it's really important in these trends. If I'm looking down a group, as we had said before, down a group does not change effective nuclear charge. You've added more protons, but you've also added another shielding shell, so it cancels out so that you have the same effective nuclear charge down a group. So you don't want to use effective nuclear charge as an argument down a group, but look at the shells. Hydrogen has only one shell, lithium has 2 shells, sodium has 3 shells. Okay, these valence electrons are getting further and further from the nucleus. So as we know, distance increases, they are not as attracted to the nucleus, and that electron cloud can expand. So going down a group, things like radius might increase, ionization energy might decrease, things that we'll look at because you're adding more shells, and that's obviously going to make the atom bigger as you add more shells. So going across a period, effective nuclear charge is an argument. Going down a group, we want to talk in terms of shells, or we want to talk in terms of distance, or we can even talk in terms of shielding. You have more shielding electrons. So here's my summary. Here's my big takeaway. Star this, circle this, do what you have to do, because this is how you're going to explain essentially every trend that you're asked about on the periodic table. If you are comparing something that goes across a period, okay, and we're really just talking about the main group elements here, there might be some anomalies that happen in the D block or the F block, but as you go across the periodic table, across a period, what is your argument going to be? What's changing? The effective nuclear charge is changing. As you go across the periodic table, if you're in just the same period, you have the same number of electron shells. So you have the same shielding electrons, but you have more protons as you go across. So the effective nuclear charge is increasing. So if your effective nuclear charge increases, then so does the force of attraction between the protons and the electrons. And you can use that to explain any trend. So across a period, effective nuclear charge, bigger charge, stronger force of attraction. So you can use that to explain radius. You have a bigger force of attraction, it pulls electrons in tighter, smaller radius. You can use that to explain ionization energy. Higher effective nuclear charge, more attraction between protons and electrons, harder to remove electrons, so on and so forth. You're going to see that this is your explanation, and you might get sick of writing about it. Okay, if we're talking about comparing things down a group, you cannot use effective nuclear charge. Don't do it. It's not about charge. Okay, down a group, your effective nuclear charge is the same thing. It's not changing, as we saw with the lithium and sodium example. Okay, you've added more shielding electrons for the same number of proton change, and your effective nuclear charge stays the same. But going down a group, what's happening? You are adding more shells. Every time you go down a group, you have a new shell that's been added. So if you have more shells, what is that going to translate to into terms of things that affect force of attraction? Distance. Your distance is increasing. Your distance between your nucleus and your electrons are increasing. So are they going to attract each other as much? No, they're not. So your force of attraction is going to go down. And again, that's going to be used to explain any trend that happens down a group, essentially. So you see, okay, going down a group, I have more shells, so the electrons are further from the nucleus, so they don't attract each other as much, so the radius becomes bigger. The electrons can get further away. Ionization energy is going to decrease. It's going to be easier to remove an electron because it's further from the nucleus. Distance, distance, distance. So you want to talk in terms of number of shells. You want to talk in terms of increased distance and how that affects force of attraction. And you can even use the term shielding in there. I have more shielding. The electrons have more shielding, so that is easier to remove an electron. More shielding, so that electron doesn't feel the same attraction to the nucleus. Okay, so you can also talk in terms of shielding if you prefer. Do not use distance or shells or shielding as an explanation across the period. Notice these are two different explanations, but you will use them time and time and time again. Okay, so again, justifying all these trends falls into two generalizations. Use effective nuclear charge to justify the trends across a period. Increased effective nuclear charge, okay, increases the Coulombic force of attraction between the nucleus and electrons. Use increased distance or greater, when I say value of n refers to the energy level. So more energy levels or more shells or shielding to justify trends down a group. Increased number of energy levels or electron shells increases the distance over which the nucleus must pull and therefore decreases the attraction for electrons. And this is going to explain all the trends that you see, because the AP is all about explaining rather than just saying, oh, this has a higher ionization energy. They want to know why. So just a couple of tips at the end. Never use a trend as an argument. So if I have to explain in terms of atomic structure, explain why neon has a higher ionization energy than O, don't say, oh, because I know ionization energy increases across a period, or this is further to the right, or anything like that. You want to explain in terms of why, okay? In a question, address both atoms. It says addressing one and leaving the other implied doesn't usually earn the point, so make sure you would talk about both things. And again, almost all of the properties that are asked about rely on the Coulombic attraction between the outer electrons and the nucleus. Okay, and remember, we know Coulombic force of attraction is related to effective nuclear charge or charge and distance.